Okay, so am I audible to all?
Yes, sir.
Yeah, okay. So let's start it. Yeah, you see my screen? I hope everybody is seeing my screen. So this is something that I thought I generally I do that in regular classes as well, that I quickly summarize whatever has been done previously, particularly in the last class or maybe last two classes. That gives us some advantage to go forward. It gives some continuity. So in the last class, which was the first one, we have seen a couple of things in briefly. For example, we have talked about spin, and also we spoke that the spin, which is an angular momentum, just very similar to L, which is an orbital angular momentum, they have the very same type of relationship among them because both of them are angular momentum. However, the orbital angular momentum are generally derived, these relationships are derived rigorously in quantum mechanics, at least the quantum mechanics that you study. For spin, that is not generally done because the quantum mechanics we do, it is not possible. So we borrow the relationship from there. So we had this magnitude of the spin angular momentum given by this particular expression, where S can actually take 0, half, 1, any value. So here L cannot take half integer values, but spin can take that. And then the Z component, if we keep this particular S into magnetic field, which is something that we'll be seeing today, if we keep this angular momentum in a magnetic field, then it will actually orient given Z components will be there, some allowed Z components will be there, and those are given by this MS. MS can take these values. So we have also therefore looked at the particular case where we had taken S is equal to half, and in that particular case MS has only two values possible, and that is minus half and half, because the values of MS always jumps with a step of 1. So if it starts from minus half, it goes to the plus half and it stops there. And we'll be talking more about these things today. And then we spoke that if we have angular momentum, either spin angular momentum or L, we should have a magnetic moment, and the magnetic moment and the angular momentum, they are proportional. We have spoken this in detail. This is called the G factor, the Landé G factor. For orbital angular momentum, it is 1. For spin angular momentum, it is the magnitude is close to 2. This is called the Bohr magneton, EH equals by 2m, and this is called gyromagnetic ratio. All these things we have done previously. I'm just noting them down one more time so that just in case you have you need to know them, it is all over here. And then we came to nuclear spin, and the nuclear spin is this particular nice feature is there, that although the nucleus, any nucleus, they are composed of nucleons, a number of protons and a number of neutrons, and all of them are spin half particle. That means for them the value of S is half, just like electron also spin half. But when they are together, their collective spin of the nucleus is not additive sum of the constituent nucleus. What does it mean? Means, for example, 13C6, correct, this particular isotope of carbon, which has 6 protons and 7 neutrons, all these 6 protons has spin half, all these 7 neutrons has spin half. So technically speaking, we might say that, well, we simply, because they are all put together, so let them add them up. So 6 multiplied by half plus 7 multiplied by half, this should give you 6.5 as a spin. But no, this 13C 6, this has only spin half. So the thing is that what's happening? What's happening? Why they are not simply getting added up? Or if fine, they are not getting added up, agreed. But what's the rule? How can calculate the spin? Well, straightforward theories are very complicated. Shell model tries to explain it using some model called a shell model. And these are the rules that the last thing we had done. So if you have odd mass number, like we have here, the 13 odd mass number, then you have half integer spin. If you have even mass number, and then depending upon whether odd proton and even proton, you have these things. So therefore, this is something that we have done last class. So if you have a nuclear spin, then well, we should have two things. First of all, as you know, for any spin, you should have a magnetic moment. So you should have a nuclear magnetic moment as well. And NMR is all about nuclear magnetic moment. So let's start from there. And if you have any problem or any questions or anything, you can certainly stop me and ask. So the nuclear magnetic moment, again, we call it just mu, will be given by, in the similar way, it has to be some G, correct? I'm not calling it a GL or GS anything. I'm just keeping it G. And it has to be E over 2m, but this time it is mp, the mass of protons, because this is nucleus that we are talking about. And for some reason, I don't know what reason, for some reason, the angular momentum in NMR is always denoted by I and not by S. So this is basically spin, which we have used the notation S previously, but any NMR book you open and you find I. So I'm just emphasizing this point further to the students, that do not get confused as if I is being something else, that we have L, then we have S, then we have I. No, somehow for NMR people, I is better than this symbol S, but they are basically the same. We still have this particular cell still have it's a nuclear spin. So we still have nuclear spin, right? Now, so this G can have different values depending upon which type of nucleus we are dealing with. This one, just before we had previously a Bohr magneton, that is something called a nuclear magneton, that is being defined this way, EH cross over 2 MP, and that is called a nuclear magneton, and that has a value of something like 3.15. Just for your record, you can write it down, electron volt per Tesla, or this can also be written as 5.05 10 to the power minus 27 joule per Tesla, just for the values. But the important thing is that this is called a nuclear magneton. The only thing which is being changed is the mass of proton over here and this G. And now the G can have different values. For example, G of proton, a single isolated proton, is 5.586, whereas G of neutron is minus of 3.826. Again, just like the spin, when we have multiple number of protons and multiple number of neutrons put together in a combined way inside the nucleus, the G that the nucleus will get out of this combination is not a direct algebraic sum of these numbers. No, they're not. Just like the spins are getting changed and it's giving something, the G of a particular nucleus will also be something. Okay, there are books you can open up and then you can have G of each of the different nuclei are given. But this is what this particular thing is. Again, cell model tries to explain why a particular G is coming for a particular nucleus, a collection of nucleons, right? But we are not bothered for that. Doesn't matter what value it is, 5.58 or 5.10, 5.7, I don't care. What I need in NMR, because this course is about NMR spectroscopy and not nuclear physics, all we need is that we should have a non-zero, let me keep it in bold, non-zero mu. We should have a non-zero mu. As long as you have a nucleus, that nucleus has a non-zero mu, that means it is acting like a tiny magnet, we are happy. And that mu is going to be equal to, some gamma times I, where I is the spin of that nucleus. Again, I told you, we always use I. And gamma is some value, so that this value will change from proton to carbon-13 to N15. Different nucleus will have a different thing. So therefore, the good thing about is that 1H, the proton that will be using most in NMR, 13C, another very important nucleus for NMR, and 15N, a very important nucleus for biology people, because 15 is part of the protein. All three of them has spin half. These are all spin half. You can check back that we have this odd mass number, correct? 1, 13, 15, odd mass number. So whenever you have odd mass number, you have spin half. It can be spin more than half as well, but half integral spin, some multiple of half. So these are all spin half. So that means we have the same spin angular momentum. However, just because gamma is different for these things, the magnetic moment is going to be different. So for the same spin, proton will have a different magnet, or it will be the magnitude of its magnetism, how big a magnet is, that's going to be different. Carbon 13 is going to be slightly lower than that, N15 is going to be even lower than that. So roughly speaking, the gamma of H and the gamma of 13C is roughly 4, whereas gamma of H and gamma of N is roughly 10. So that means that although 15N and 1H, both of them are spin half, but their magnetic moment, which is important in NMR, is 10 times higher for proton than the nitrogen, and 4 times higher than the carbon. That is why proton is sensitive. So there are other reasons for this being sensitive. So that's something that I'll be talking about. However, one reason behind that proton is very sensitive is that it has a big magnetic moment. It is a stronger magnet, and therefore it has its own benefit. So that is directly coming from gyromagnetic ratio. So we have got our quantum mechanics has said that, well, we have a relationship like this, and also quantum mechanics has also said that if we have I, which is spin, correct, that spin angular momentum should have this particular relationship. So this I plus 1 H cross, and IZ is M H cross, where M goes from minus I all the way to plus I. Fine, this is fine, but how it is this thing is important for NMR? This way. So what this particular thing is, this IZ, the IZ is that if we somehow keep this mu, this magnet, correct, it's just a magnet, although this quantum mechanical magnet doesn't have a north pole, south pole like this, but still it is a magnet, it interacts with magnetic field. If I try to draw a direction, like this is basically a B0 or B, the magnetic field, right? We have to bring magnetic field in NMR anyway, slowly. And I assume that this, suppose this is basically some B0 as a magnitude, and then it is in the Z direction. So I can write it this way, correct? It's a Z direction magnetic field. If I now keep this magnetic moment inside here, this will orient, this particular thing is orient according to this particular direction. So this direction, it becomes the Z direction. So whenever we always, in fact, I ask many times that the students that, well, you know, this is spin or angular momentum, and this IZ, Z component. Fine, this you have got Z component, the formula is MH cross, but which is the Z direction? Show me. If I give you a hydrogen atom, for example, you have an electron, what's the Z direction? Z direction is not defined as long as you are not switching on a magnetic field or an electric field. Electric field is not important in NMR, a magnetic field is. So the moment I switch on a magnetic field, that direction, whatever direction, that is my Z direction. I define that is my Z direction. And then with respect to that, this magnetic moments we're going to align. Now question is that, is it going to align in this way? So let me try draw with a blue. If this is one, then is it going to align in this way? This is going to be my mu. Correct? So what happens is that we have seen that if I have a magnet which has a north pole and a south pole, and if I switch on a magnetic field here, some B, immediately this, what happens is that immediately this north pole goes like this, south pole goes like, so it will align. So after some, immediately we'll see that now it is aligned like this. Right? It is completely aligned. So is it going to be doing the same thing here? Because of course it is also a magnet and we have a magnetic field. The answer is no. And where from we are getting this answer? We are getting this answer from this two relationship that the quantum mechanics has given us. What is the biggest Z component? The biggest Z component is when M takes the largest value, right? And the largest value is plus I. So therefore, the largest Z component is I. right? IH cross. So what happens is that I find it that the magnitude has this as the magnitude has this as the component, correct? This is this into IH, this into H cross, and the largest Z component is IH cross because M has the largest value I, correct? So, and then this particular quantity is even larger than I, because if you do not have this 1, then it's I square root of I square is I, fine, but we have I into I plus 1. So because of this 1, this quantity, this whole quantity is larger than I, which is the largest Z component. That means that quantum mechanics will never allow this to happen, right? What will happen is that this, let me just copy this part, I don't have to draw it again. Correct? So this will not happen. Instead, it is going to take an angular direction, right? Because if it is an angular direction, then this length is root over I into I plus 1 H cross, whereas this direction, this length is maximum can be IH cross, right? And therefore the angle is always going to be more than 0, correct? It will never align. So quantum mechanics doesn't allow it to align completely with the magnetic field. It will always keep certain angle, and those angles are also defined because it cannot just take any particular component. It has to take a component like IH cross and then I minus 1 IH cross all the way to minus IH cross, correct? So these components are discrete components are going to be there. So therefore, if I have the alignment, and the alignment is going to be either this one or this one or this one. So there are discrete alignment, and this is called, this has a name. This is called space quantization. Because this is so different than our classical world. Because if I have a magnet, correct, this magnet, first of all, it is allowed to completely align with the magnetic field. The north pole is going to be here, south pole is going to be here. It's going to be exactly aligned this. First of all, that is not allowed. Second, any angle, I can basically keep this magnet into any particular angle forcefully, and then it is allowed. But here this magnet is only be allowed a certain direction where this Z component is defined, right? So this is quantum mechanics is very different. Now the question is that we have found this. So because of this particular thing that we have an angle between this, two profound things will happen, and that will actually constitute the basis of NMR spectroscopy, the theory of NMR, right? Without going into much detail, I'll be going through this. And what are the two things that will happen? One is that this, I have just drawn this previously so that we can save some time. So two things will happen, and one, and let me just write down those two things. One, because of this angle here, it will experience a torque. I'll explain this. This picture is all about that torque. And second, what happens is that because this angle is that, so therefore there'll be a potential energy that's going to be discretized. Why? Because we know that whenever we have a particular magnet, and that magnet is making any type of angle with this magnetic field, it has certain potential energy, interaction energy between them. The interaction energy is minimum when it is completely aligned, but well, quantum mechanics is not allowing it to completely align, but whatever it is, this is going to be more or less aligned than this one, which is anti-aligned. So therefore, as this particular orientation going from one to this to this to this, it is the number, and it is going from mostly aligned to mostly non-aligned, the interaction energy is going to be changing. So therefore, as these states are discrete, the potential energy is also going to be discrete. So this is this particular torque is going to give us a very important thing. It's called Larmor precision that we'll be learning now. This torque is going to give a Larmor precision, which is very important in NMR, and this potential energy discreteness will give us Zeeman splitting, which is also very important for NMR. So let's learn one by one what happens in these two. Okay. So here I have assumed in this particular picture, I have assumed that the gamma is positive. Now, the gamma can be either positive or negative depending upon which nucleus you're talking about. Like, for example, 1H and 13C, they have positive gamma. However, N15 has a negative gamma. So what gamma is going to be, the value as well as its sign, whether it's going to be positive or negative, that is not NMR's job to determine. It is determined by some nuclear mechanism inside that's happening, and we are not bothered for that. However, I have to draw this picture either taking positive or negative. So generally it has been done taking positive gamma, because 1H proton, which is the one which is will be mostly performing, has positive gamma. So I have just drawn this. So what happens is that if I have a situation like this, go back here, like for example, no, not this much, here. So I have mu and gamma. So if gamma is positive, then this vector I and this vector mu, they will point into the same direction. If gamma is negative, then I and mu, they will be pointing into the different direction, opposite direction. So as I have taken positive gamma, so I have drawn this way. So suppose this is my mu, and there's a theta. This theta is some theta which is defined by quantum mechanics. It cannot be zero. And therefore, it has corresponding I. And now this I is now switched on a magnetic field, and at this magnetic field, you can assume this magnetic field, maybe this is a z direction. So we can think about, we can write it down that this is my z direction. Right? This is my z direction. So let's see what happens. First thing, as this a torque is going to be applied to it, and this torque is going to be something like this. Tau, torque is represented by tau, and the torque is going to be mu cross b. So this is something that we know from our classical physics as well, that if we have magnetic moment and then if you have a b, right, then the torque that applies is basically mu cross b. So you can check that in this classical picture as well. So for example, let me draw this in a slightly better way. So suppose you have this as your North Pole, and this is your South Pole. This is North Pole. This is South Pole. And if you have a magnetic field, so this North Pole is going to experience a force in this way. South Pole is going to force in this way. And you can see that if you have a situation like this, and this is the force is on this side, another force in this side. So what will happen is that this will start rotating, right? This will start rotating. So this is the torque that is going to be applied. So therefore equal amount of force applied, and that force is actually separated by this much. So therefore it should give a torque in this direction, and therefore this N and S is going to be aligned. That is the reason a magnet actually aligns with the magnetic field, this torque. And see, the same torque we're talking about, mathematically it is called mu cross b. Now I can now write down, because I know that mu is gamma I, so I write gamma I cross b. Right? So I write gamma I cross b. Also, another thing we know from classical physics is that the torque is equal to rate of change of angular momentum. Either spin angular momentum or orbital angular momentum, doesn't matter, angular momentum. Very similarly, as force we know force is the rate of change of linear momentum, correct? We know that in a force is a rate of change of linear momentum. Similarly, a torque, which is a rotation rotation is involved there, is rate of change of angular momentum. So therefore, tau can also be written as, that tau I can written as di dt, rate of, so why di dt? So I is the angular momentum, here it is spin, and di is the change in I, and dt is the change in time. So therefore change in I divided by change in time, so that is the rate of change of I with respect to time, and this is tau, correct? So therefore we have got this particular thing. But we have already found out from this expression for the magnetic moment thing that gamma I cross B is tau. So therefore, I guess want to equate this. This is going to be gamma I cross B. And we can see that what's the angle between I and B? The angle between I and B is theta. So therefore, I cross B, the magnitude of I cross B is just going to be is equal to gamma I, the magnitude of I, B, the magnitude of B, and then it's going to be sine theta. Correct? That's because cross product is the two vectors magnitude multiplied by sine theta. So we have understood that tau is equal to gamma I B sine theta. Agreed. Now comes here. So what happens is, if I have a situation like tau, which is I cross B, let's see which is the direction of I cross B. So I have I in this direction and I have B in this direction. So I cross B is going to be along this direction in the tangentially. So it's basically a tangent. If we just keep a tangent here, that is going to be the direction of I cross B. I cross B in this direction, this particular direction. And therefore, this tip is just going to be pushed a little by this particular torque, and then as it is, the direction is, the tip is changing, the torque is also going to change its direction. So eventually what happens is that this torque will continuously make this tip to rotate in this particular fashion. That is what I have drawn by this particular two arrows, that this tip is going to be rotating in this direction. So that is going to give us a precision. The precision is coming. But before that, I have just drawn this way. So suppose this I has reached from here to here, so that this is basically a very big one I have drawn. Otherwise, you cannot understand it. But the thing is that this change, the amount of change which I have drawn in red, is di, the change of I. That is basically a di. So therefore, I plus the di vector is going to be the new I. If I just try to draw another one, this is going to be the new I, which is basically this particular position. So therefore, this is the di. And then from the geometry, we know that this is just a small arc, very small arc on the circle. So therefore, this di, the length of di, is given by this particular radius. The radius is I sine theta, because this whole thing is I. So therefore, this radius is I sine theta, and I sine theta, and this is a small angle d phi. So therefore, di is equal to I sine theta d phi. So that is something that I'll be writing. Now I'll be writing this, that the di, right, this particular thing is I sine theta d phi. Right? So if I just take now a di dt, for example, from this side, right, di dt, I find that this I is given, the length is not changing. So this is going to be just d phi dt, right? Because I is fixed, theta is fixed, it is given by quantum mechanics. So therefore, this particular thing. But already we know that the torque is di dt, right? So di dt is already given this one. So therefore, from geometry, we find that di dt is this one, whereas from the other side, we have found that the di dt is given by this one. So therefore, I just simply equate this. So I just equate this. This is going to be gamma times I times B sine theta, correct? And then the sine theta and then sine theta will cancel, and this I is going to be cancelled. So I find here d phi dt as my left side, and gamma times the magnitude of B on my right side. But what is d phi dt? The d phi dt is the rate of change of this angle, and that is angular rotation, angular velocity, correct? So therefore, this d phi dt is nothing but the omega, which is the change of angle, right? Like linear velocity is change of position, rate of change of position. Similarly, angular velocity is rate of change of angle, correct? So therefore, this d phi dt is the rate at which this tip is moving, and therefore this. Now this particular thing is this omega is equal to gamma times B, and often that magnitude wise it is written in omega 0, because this B is written as gamma times B0. So this B, when the B is basically B0 into the Z direction, right, then the magnitude wise, then we write this particular thing, omega 0 gamma times B0. And this, what is this omega 0 is about? What speed it is? It is speed in which this tip is rotating across this circle. So therefore you have this particular magnetic moment, and this magnetic moment, the tip is going to be having a torque, and that torque will make it precise like this. So the torque is going to be a precise like this, and this precision frequency is going to be proportional to the gamma and the proportional to the magnetic field we are using. So this is called Larmor precision. So this is called the so we have slowly have got to this the Larmor precision, and Joseph Larmor was the person for which this Larmor precision is the name has been done. So this is this particular thing. But now this is the magnitude. Gamma omega 0 is equal to gamma b0, where b0 is the magnitude of the magnetic field. Everything. What is the direction? So the direction of omega, we can see that if this particular tip is rotating in this way, right, then obviously the if I just have this rule, the thumb rule, if it is moving this way, therefore the omega is going to be directly the downward. So it is opposite to the direction of b. So in this way, it is for positive gamma, it is basically the omega is downwards because it is moving in this particular direction. So we can write it down that omega as a vector is minus gamma times b as a vector. So therefore, this is the relationship that we get, that the omega vector, right, not only the magnitude but the vector, is having a negative sign here. Now the question is that if we have a negative gamma, then this negative gamma will cancel with this negative sign, and in that particular case what will happen is that the omega and b will be in the same direction. That means the rotation sense of rotation is just going to be reversed. In one case, this particular case, we have positive gamma and it is rotating clockwise for positive gamma, but then it's going to be anti-clockwise for negative gamma. But that's very subtle difference. We do not bother for that much, unless of course you want to do research on NMR pulse program or something. You go deep into this subtle thing, that is a positive gamma, negative gamma. You don't have to bother for this. So we have understood the quantum mechanical explanation behind the Larmor precision, correct? We'll be coming to this Larmor precision frequency and Larmor precision later as well. But before that, I have a second job, and that job is this particular potential energy discreteness, and that particular thing is that we'll be going to do next. If you have any questions till whatever we have done up to here, you can ask me before I start something else. Potential energy, okay, fine. So before potential energy, I have prepared something for you. I'll just want to give you some flavor of numbers, which because we have got this particular discussion, I'll give you some flavor of numbers. So what is that? So this gamma, which is important for NMR, any person who is learning NMR, this gamma, gyroscope ratio, is extremely important. So let's talk something more about this gamma. What gamma has this unit? What's the unit? So it has two units. One unit is radian per second per Tesla, and another unit is Coulomb per kg. This is very weird, isn't it? One is radian per second per Tesla, correct? Which is, I can understand directly from here that why radian per second per Tesla is coming, because I can write down this particular equation directly as a gamma, correct? Forget about the plus minus, the magnitude of gamma is somehow having omega divided by b, correct? So omega divided by b, that is coming directly from here. So omega has a radian per second as a unit, b has a unit of Tesla. So obviously the gamma has an unit of radian per second per Tesla. That makes sense, correct? But Coulomb per kg, where from this is coming? This is really weird. However, we understand that where from Coulomb per kg is coming, we'll not be understanding the next step, that where from the Larmor frequency that we are talking about, like we have a 400 megahertz spectrometer. This megahertz, these numbers, megahertz thing, will not be properly understood unless we understand where from this Coulomb per kg is coming. So let's try to understand this a little bit. And for that, we need to understand the definition of Tesla. This is not the same Tesla of the car that we are now talking a lot of Tesla cars. No, this is simply magnetic field Tesla, one Tesla. So the idea is, the definition says that if a particle, so let me write it down, if a particle carrying 1 coulomb of charge, so you have a particle that has 1 coulomb of charge, what it is doing, it is passing through a magnetic field perpendicular to its direction. So I have a particle, 1 coulomb of charge is there in that particular thing. It is passing through a magnetic field. If the velocity is like left to right, then the magnetic field is up and down. Right? It's perpendicular to the direction of magnetic field. Then in that case, it will experience a Lorentz force. It will experience force. I have told this in the first class. This is the reason I told that particular experiment in the first class, that if you have magnetic field, then it experiences Lorentz, it experiences force, and that's called a Lorentz force. So if it's happening like this, a particle carrying the 1 coulomb charge passing the magnetic field experiences a Lorentz force of 1 Newton. If the Lorentz force is exactly 1 Newton, then the magnetic field is defined to be 1 Tesla. So that is the formal definition of 1 Tesla magnetic field. How much magnetic field is 1 Tesla? The magnetic field 1 Tesla is that if we have, that means the 1 Tesla means that if we have, so if you have 1 Tesla magnetic field, if you have a particle having 1 coulomb of charge and it is moving with 1 meter per second velocity, then this will give a Lorentz force equal to 1 Newton. That is basically the expression. This expression is giving you 1 Tesla. Now let's see what happens is that now Newton is force, so therefore a force can also be written in terms of mass into acceleration. So therefore 1 Newton can also be written as kg, which is mass, into acceleration, which is meter per second square. Correct? That is force. Correct? So this two should be equated. So if we just equate this two, I find that the Tesla becomes equal to kg meter per second square multiplied by second multiplied by multiplied by 1 over coulomb into meter. So therefore all together is getting kg divided by second and then coulomb. So this is something that is happening. So if this is my Tesla, then what is Tesla per second? Radian doesn't have any unit. So therefore this 1 unit that we have understood from here is per Tesla per second. So let's see what happens is that per Tesla per second. So therefore per Tesla per second comes out to be something like, so directly from here we get per Tesla, that is inverse Tesla, is second coulomb divided by kg. So therefore per Tesla per second is coulomb by kg. Correct? So therefore we find that the per Tesla per second and coulomb per kg are basically the same unit, although it might look like that where from kg is coming. kg is actually coming from there. So therefore, you should remember this part Tesla per second, which is a natural unit of gamma, because it is defined from this particular relationship, correct, is also equal to Coulomb per kg. And you will be shortly understanding why this particular relationship is important to know in NMR. So let's go back to the thing that what we are doing. So for let's start from the electron, because we have started from electron. So the electron has this particular situation, electron omega e, the Larmor frequency. Suppose you want to calculate the Larmor frequency of electron in certain magnetic field. So that's going to be gamma times the B, and gamma is going to be some GS, which is close to 2. I told you in the last class, E divided by 2 times m of E, mass of electron, and then the B, correct? So if I now take suppose 1 Tesla of magnetic field, then let me see what this particular thing is. So GS is 2, close to 2, but I just take it 2. Then the electronic charge is 1.602 10 to the power minus 19 Coulomb, right? And I take B to be 1 Tesla. So I want to try to find out what is the Larmor frequency of electron in 1 Tesla magnetic field. Then I have another 2 coming from here naturally. This 2 is here, correct? And then I have 9.1 10 to the minus 31 kg as my mass, right? So what we find is that I have some numbers definitely will come from here. This number I'll be telling you what number. The number is, let me write it down. So if you just have a calculator, it's going to be something like 1.76 10 to the power 11 Coulomb per kg into Tesla, right? Now Coulomb per kg has come, but we already have seen that Coulomb per kg is part Tesla per second, correct? So this is this one. So I'll be using this now so that you understand what is happening. So therefore, this is going to be 1.76 10 to the power 11 per Tesla per second into Tesla. So Tesla is going to be cancelled out, and it's going to be per second. So therefore, it is going to be hertz. Actually, basically it's radian per second. Radian doesn't have it, so it's going to be omega is radian per second. So therefore, you get this is this much amount of radian per second. So is the Larmor frequency of electron in B. So, but the thing is that how much is that? Let's convert it into a normal frequency. So nu of E is going to be omega of E divided by 2 pi, and if you just do this, it is going to be something like 28.025 gigahertz. So you just take this value, correct, and divide it by 2 pi, which is about 6, divided by, and then this is going to be radian per second. Earlier it was, because cancelled of t and my t to the 1 is 1. So this is radian per second, and that will be hertz. So this. So therefore, we see that the Larmor frequency of electron is in gigahertz, and that is why EPR machines. So although it is a course of NMR, but EPR is the working frequency of any EPR or ESR machine is in gigahertz, not in megahertz. Megahertz are NMR machines, 400 megahertz, 100 megahertz, 200 megahertz. But EPR machines are gigahertz, because in EPR, they do not work with the nuclear spin. They work with electron spin, and electron has, for the same 1 Tesla magnetic field, has a much, much larger Larmor frequency. Why? That's because they have this tiny mass here. The moment I'll be changing this mass with the mass of proton, which is heavier, this whole denominator is going to be bigger, and this omega is going to be going from gigahertz to megahertz. It will come down. So let's do that to have an idea that how this NMR thing is done. So let's now do for a proton. So proton is omega p, and that is going to be gamma times b again, but then gamma is going to be some g of p e, and then 2 times m p. Now that will change, and therefore this we can find out. So g of p is 5.58. I have already told you before, the g of the Lambda g factor of proton. And then we have so basically we can write it down this way. I have just written this way: gp multiplied by mu n over h cross, and then b. Now B is already there. B. So I have just used these values. Mu1 has a value of 3.15 10 to the power minus 8 electron volt in Tesla, then multiplied by 1 Tesla because the B, and then 6.58 10 to the power minus 16 electron volt second. That is H cross in electron volt second. So these are the numbers, and then finally what you get is that what is important is 2.67 into 10 to the power 8 hertz. So we are basically converting it back and directly converting it to hertz. If you convert this whole thing into hertz, correct? I have done it in 2 steps there, but it is having this. That means this particular. No, sorry, I'm sorry. This is per second, so it's basically radian per second. Now, if I just convert this into a nu of proton, and that's going to be omega of proton divided by 2 pi, and that's going to be something like 42.58 megahertz. So if I just take this value, so earlier this value was in 10 to the power 11, but here it has a value on 10 to the power 8. It has come down a factor of 3. That is why you are going from gigahertz to megahertz. And this, that means that if you have 1 Tesla of magnetic field, you have Larmor frequency 42.58 megahertz. So therefore, if I have a NMR machine which has 1 Tesla magnetic field inside, then we'll be calling it as a 42 megahertz, roughly 42 megahertz NMR spectrometer. But generally, we do not have 42 megahertz NMR spectrometer. We have, for example, in NISR, we have a 400 megahertz spectrometer. And in 400 megahertz spectrometer, we can calculate using this thing that what's going to be the magnetic field. And this is going to be 400 divided by 42.58. And this is going to be something like 9.39 Tesla. That's a huge magnetic field. So inside a 400 megahertz spectrometer, we have 9.39 Tesla. Now, why it is called 400 megahertz spectrometer? Because at 9.39 Tesla magnetic field, the Larmor frequency of an isolated proton is going to be exactly equal to, so this particular quantity is going to be exactly equal to 400 megahertz. That is why we call. So therefore, the name of a spectrometer, 400 megahertz spectrometer, comes from this particular value. Right? Ideally, that means that everything is same. Gamma of proton is given everything. So therefore, the gamma is given, that we cannot change. So from 400 megahertz spectrometer to 700 megahertz spectrometer, the only thing which is changing is basically this B, correct? So instead of saying that we have a 9.3945 Tesla spectrometer, we call it 400 megahertz spectrometer. It's easy, just it's easy. Anyway, so this is basically, I just thought of, I quickly drawn today a few numbers so that it gives you a perspective that for the same magnetic field, electron has a Larmor frequency of 28 gigahertz, whereas a proton has a magnetic Larmor frequency of only 42 megahertz. And that is why NMR runs in megahertz. Correct. So the last statement that I can tell in this particular case is that NMR runs at megahertz. So whether it's proton, carbon, everything, all the Larmor frequencies are going to be roughly close to a few megahertz. In fact, now you can actually tell that if we have a 400 megahertz spectrometer, right, what is going to be the Larmor frequency of carbon? It's going to be about roughly 1/4, so it's going to be 100 megahertz, correct? But still, we will not be calling it a 100 megahertz spectrometer. We always call the name of the spectrometer as the Larmor frequency of proton. Okay, so this is nearly 4:53. The small thing that I'll be doing, maybe another 4 or 5 minutes, because we started 5 minutes late. And quickly, I'll be taking the potential energy thing, and then we'll continue next class about that particular thing. So the second thing that we had is this potential energy. It is given that the energy, interaction energy E between a magnetic field and a magnetic moment is given by minus mu dot B. You can clearly see that the mu cross B, the cross product, mu cross B was the vector, mu cross was the torque, whereas mu dot B, dot product, is going to be a scalar quantity after taking the dot product between two vectors. That's going to be the energy E. So therefore, we can write it down this way, that this particular thing is minus mu z b0, because I know that if the b is suppose is only along b0, along z direction, correct, the way we have taken it, so therefore it is only the z component of mu that is going to be there, because that is the rule of dot product. And I now know that mu z is going to be gamma times iz, the z component of angular momentum, and then it's going to be 0, because this is happening because mu is gamma times I. And now we know that Iz is given by mh cross, different values of m. So therefore this energy is going to be minus gamma mh cross b0. But we have just learned that, where we have learned it somewhere here. So we have just learned that the magnitude of gamma multiplied by magnitude of b, put together everything, is basically the Larmor frequency omega. So what I'll be doing is that I'll be writing this, I'll be taking gamma from here, b0 from here, and I'll be putting this into a Larmor frequency thing, and therefore I'll be writing this as a minus m omega 0 h cross, where omega 0 is gamma times b0 magnitude wise. Right? So I'll write this particular thing. So now we have the E that is depending upon M. So that is why we often write that not only E, but we write E as a function of EM, and that is minus of M omega 0 h cross. That is the two levels. So if we have now M goes from minus half and plus up, only two values it can take, because it's a spin half like proton or carbon 13, it's a spin half nucleus. Then we have M goes to half and minus half, correct? And clearly, because we have a negative sign over here, so when you have take m equals plus half, that will give me a lower energy, and when you have a minus half, so this minus and this minus will cancel, and therefore we have a larger energy. So therefore what happens is that we can draw in this way. So we'll be having a split like this. So this is m, higher energy is for minus half, m lower energy for half, and this will be two energy levels, and this energy levels, this is called E minus half, and this is also called E half. In few books you will also write down that E, this is called E beta, and this is called E alpha, because this particular state M plus, this is called the alpha state, alpha spin state, and minus is called the beta spin state, E alpha and beta, and then the difference between these is the energy as basically delta E. That is going to be the difference between the two, and that is going to be half omega 0 h cross minus omega 0 h cross, and is equal to omega 0 h cross. So therefore it will be two levels, two energy levels, the moment you have this particular magnetic field, and these two are called the Zeeman level, the Zeeman splitting. So this split, the moment you have the magnetic field on, because this omega 0 has magnetic field, if the magnetic B0 is 0, that means no magnetic field, then omega 0 is 0, no Larmor precision. If there's no Larmor precision, then the difference between these two energy is delta E is 0, because omega 0 is 0. So therefore these two levels will basically collapse to one single level. So this splitting of energy level is coming only in presence of magnetic field, and this splitting is called Zeeman splitting, and this is very important, and we'll continue from here next class that what happens that we have a Zeeman splitting and other things. So we have learned two important things today, that if we have a nuclear, if you have a nucleus which has a non-zero magnetic moment, that magnetic moment, the moment you put that whole thing inside the magnetic field, that means you are putting inside the spectrometer, two profound things happen. One, the magnetic moment, the vector magnetic moment, start precessing, and it will precess with certain angle that is going to create with the B0, and that angle is going to give a proper level. So therefore, if you just try to draw it, if you have this is your magnetic field, right? So one is going to be like this, and that is going to be having a precision like this, right? Another one is going to be like this, that is, this is going to be the m goes from m, the upper one, minus half, and this goes to be m equal to half. So this is the other one. So for this is basically the half. The aligned one is going to be lower energy, and then this is going to be precessing in this particular fashion, in making another loop. So therefore, we have this particular one making a precision like this. These ones are going to be precision like this, and they will be having this precision frequency given by omega 0. The precision frequency is going to be the same, but this orientation and this orientation will have certain energy difference, and this is given by this. So I stop here. If you have now questions, you can ask me. So yeah, it's exactly 5. So we have taken 55 minutes. You can now ask me questions on this topic. Hello.
Yes, participants, if you have any doubt, any questions, please you can type into the chat box. Please type it, because you may not be able to speak, but you can type. Yes. In YouTube पे देखो. Attendance are. Participants, appears to be that there is no doubt or any question, Professor Ghosh.
Yeah, it's fine. No problem.
Yeah, I think it is very clear, so that I think they have understood it nicely. It appears to. Any doubt? So they are telling that at present they do not have any doubt. Anyway, if you have any doubt, you can put those doubts in the next class, in the beginning of the next class, so that professor can clarify.
Or
Okay?
maybe you can mail me actually.
Yes, you can also send email.
So
Okay.
this is my email ID, ARINGH at NISER.ac.in. So this is my email ID. You can send me your doubts, and I collect those doubts, and I'll clarify those doubts at the beginning of next class. So whatever doubt you have, you might have any particular doubt.
Not
Just
only necessary in this class, even previous class also.
so and also just make sure that the subject line, you just make it HBNI NMR, so that I can separately sort them. I can find those emails. I get too many emails per day. So you can just simply HBNI NMR course or HBNMR, so then I can find it. So you mail me. It is not really necessary that immediately after the teaching you have to ask me questions. Sometimes it's not possible, but go back and check. And I'm going to share this whiteboard anyway. So then you can ask me questions, or you can send me emails. Okay. Yeah.
Okay, so if there is no question, okay, thank you, Professor Ghosh. Thank
Yeah,
you very
sure.
much. So that we'll start on Thursday.
Yeah.
Tomorrow, Thursday at 4 o'clock.
Sure.
Okay. Okay. Thank you very much.
Yeah. Thank you. Bye-bye.
Thank you. Bye.